This is Module 4, the physical layer, part of the Introduction to Networks version 7.0 of the Cisco Academy curriculum. Before any network communications can occur, a physical connection to a local network must be established. This connection could either be wired or wireless, depending upon the setup of the network. This generally applies whether you are considering a corporate office or a home office. The host computer must have a network interface card that connects to the particular type of network that you have. In wireless, you may have 802.11a, B, G, and AC, or one of the other platforms. The NIC card that you choose should be able to connect with whatever you have as a wireless access point and whatever you have as the particular standard. Some devices have just one NIC, while others may have multiple NICs, wired and or wireless, for example. Today, most laptops come with both wired and wireless. Not all physical connections, though, will offer the same level of performance. You could have a 1 gigabit router in your home or business, but if your network card is only 100 meg, that's the top speed that you will get. It is also inversely, if your laptop has a 1 gigabit card, but your network is only 100 meg, again, that is the top speed that you will get. The physical connection is extremely important to us because this is the layer that is closest to the end user. This is where the majority of problems in a network occur because of people plugging their network cable into the wrong outlet, tripping over, accidentally cutting or damaging the network connections in some way. At the physical layer, we transport bits across the network media. This accepts a complete frame from the data link layer and encodes it as a series of signals that are transmitted to the local medium. And this is the last step in the encapsulation process. The next device in the path to the destination receives the bits and re-encapsulates the frame, then decides what to do with it. As we take a look at the diagram, we can think of a block of data coming from a program that we may have, and it comes down to layer 4 of the OSI model. At layer 4, this large piece of data may be segmented for transport over the medium. One of the segments will come down now to layer 3. Layer 4 has already attached to it a header with the port number for the type of data that we're carrying. So when that comes down, the actual data and the header are seen by layer 3 as solely data. Layer 3 does not know about the header that layer 4 put on, indicating the port number for the protocol that we are using. So it sees the entire segment as a piece of data. Layer 3 will add on the IP addressing. It then sends it down to layer 2. Layer 2 sees the entire packet that we get from layer 3, again, as data. It has no knowledge of IP addressing. It has no knowledge of the port numbers that were put on at layer 4. It is seen solely as data. At layer 2, depending upon the technology that we are using, we would add on some type of layer 2 heading, as well as usually a trailer encompassing a frame check sequence to see if the frame arrived correctly. This is all then sent down to the physical layer. The physical layer will now encapsulate all that data, including the headers that were put on at layer 2, layer 3, layer 4, and it will encode it as a series of ones and zeros. And send those out via electrical signals, wireless signals, optical signals, for whatever type of medium that we may be using. At the physical layer, we have many organizations that regulate the standards for physical connections. And when I say physical, I also include wireless. The ISO, the EIA-TIA, the ITU-T, ANSI, the IEEE. Each one of these organizations will set the standards for a particular type of communications. The IEEE, for example, controls wireless, IEEE 802.11. This makes sense so that the standards set for a physical connection, whether it be Ethernet, serial, satellite, optical, the standards are the same worldwide. Recently, we have had an example of what would have happened if we had more than one standard for a particular type of connection in the area of high definition DVDs. Originally, you had high def DVDs and high def DVD players under a standard established by Toshiba. You also had Blu-ray, both discs and players, under standards set by Sony. Both were available to the public. Blu-ray is the one that caught on, and now you no longer see high definition. This has happened in the past with tape, VHS versus Betamax. In that case, VHS won out over Sony's Betamax. So it makes sense to have only one organization controlling the standards so that worldwide interoperability remains constant. At the physical layer, the standards will address three functional areas. The physical components, such as the size, the connectivity, the amount of power that a physical component can handle. The encoding techniques that we may use. And there are many types of encoding techniques. And how do we signal? How do we signal that we are going to send data? How do we signal that it is the end of the data? So physical components, encoding, and signaling all take place at the physical layer. The physical components are the hardware devices, media, and other connectors that transmit the signals that represent the bits. Hardware components like NICs, interfaces and connectors, cable materials, cable designs, they are all specified in the standards associated with the physical layer. When we encode a signal, we could encode it as pulses. And this could represent a 1, a 0, and maybe this could represent a single 1, or maybe this could represent two ones. When it comes out of a line from transmission, it does not look as clean as this. So we needed to find a better way to transmit data. One of the most common is Manchester encoding. Manchester encoding says that if I have a transition that goes from low to high, it is a logic 1. If I have a transition that goes from high to low, it is a logic 0. As we can see in the diagram, we have a transition from high to low as a logic 0, low to high as a 1, low or high to low as a logic 0. We then need to return. We have another transition from high to low for a logic 0, low to high for a logic 1. Again, we need to return, and a transition low to high for a logic 1. Now, most people would think that this is a little bit confusing, but if we take a look and think about this, if I just draw a dotted line, saying that anything between that dotted line we ignore as a transition. It now allows our signal to vary a slight amount. Because even though one side, and just taking a rough number, one side may send out data with a 9600 baud rate, and theoretically, the other side should also be 9600. Are they exactly 9600? Probably not. Maybe this one is 9575. Maybe this is 9630. Having this area between those two dotted lines allows us to adjust for a difference in the timing and allows us to send only the signal without a separate timing pulse connected to it. Some of the other encoding methods are 4-bit, 5-bit, and 8-bit, 10-bit. There have been many more over the years, and all used for particular purposes. If I took a look at a binary number, 0, 1, 2, 3, and 4, and then examine what the gray code would have looked like. Gray code would be 0, 1. And at this point, most people say, well, it looks to be the same. This is where it differs from the binary. 2, 3, and 4. Most people would say, why? Why did we use the gray code? And if we look between any two consecutive digits, only one change actually occurs. And this was built specifically for the days when electronics were not as complex and as accurate as they are today. And we needed a code that eliminated a great deal of possibilities of an error occurring. In today's world, the gray code is no longer needed, but I show it here to give you an idea of the development of codes and why particular things happen. Here are some other types of signaling, some of which you may be familiar with. This is just a voltage signal in that we go from a low to a high. The high represents a 1, the low represents a 0. We could also change the voltage in amplitude modulation, meaning that a low would be at one amplitude, a high would be at another amplitude. AM radio, for instance. Frequency modulation, such as in FM radio, you notice a difference in the frequency. This is a much slower frequency versus a much faster frequency, indicating the slower, indicating a logic 0, the faster, indicating a logic 1. The last one shown here is pulse modulation, in that where do I start the actual pulse? Here I'm starting it on the upswing. It gives me a logic 0. Here I'm starting it on the downswing, a logic 1. With modern technology, we could take a sine wave and say, here represents 0, 0. If I start here, 0, 1. Coming down, 1, 0. And below, 1, 1. And then we'd be back to 0, 0. So with pulse modulation, we could get a little bit more accurate. And as technology evolves, we probably will. One of the things that you may notice is that we do not go all the way down to 0, which is referred to as cutoff, and we don't go all the way to the maximum voltage, which is referred to as saturation. We work in between those two levels. The reason for this is it makes the switching much faster. Think of yourselves in a car and you want to accelerate by 10 miles an hour. It would be much faster for you to go from 10 to 20 versus 0 to 10. So we never drive all the way down to 0, and we never drive all the way up to the maximum. As we can see here on the left, we have a step pattern. A step going down could be a logic 0. A step going up could be a logic 1. As we send light pulses, it can also represent ones and zeros. When we talk about bandwidth, bandwidth is the capacity at which a medium can carry data. Digital bandwidth measures the amount of data that can flow from one place to another in a given amount of time. How many bits can be transmitted in 1 second, bits per second, as shown here, BPS. Many people confuse this with bytes per second. No, it is bits per second. If you wanted bytes per second, you would need to divide by 8. The physical media properties and the current technologies and the laws of physics play a role in determining the available bandwidth. How fast can we move data across a particular line? Some of the abbreviations that we use, and this is referred to as metric notation: kilobits per second, which is 1,000, megabits, 1 million, gigabits, 1 trillion, and so on. So kilobits, megabits, gigabits, terabits. And this is all going to the left side from the decimal point. So if this was my decimal point, as I move over 3 bits, this would be capital K. If I move over 3 more, this would be capital M. 3 more, would be capital G. And if I went 3 more, that would be in terabits. So it gives us a shorthand way of writing down without putting in all the zeros so that we know the speed. Going to the right from the original decimal point, if I went 3 bits, that would be small m for milli. If I go 3 more, that would be a small u for micro. 3 more, that would be a small n for nano. 3 more would be a small p for pico. Many components you will see labeled with these metric notations. We would also be looking at this if we wanted to know the pulse width of a particular frequency. Now, when I send data, nothing happens instantaneously. So we have latency, which is the amount of time that includes all the delays for the data to travel from one given point to another. We may have physical delays, processing delays as it goes through devices, or just delays as it goes through a particular medium. The throughput is the measure of the transfer of bits across the media over a given period of time. But this includes both the data that I want to send as well as the overhead that was put on by the multiple layers of the OSI model. So the actual data could be a very small amount of the total throughput. The data that we are trying to send is referred to as the good put. and that is the measure of usable data transferred over a given period of time. When you order a package, the package or what you have ordered arrives in a box. That is the overhead. The actual item that you ordered inside the box, that is the goodput. The throughput is normally discarded. Copper cabling, which is the most common form of cabling at the physical layer, is very inexpensive, it's easy to install, and has low resistance to electrical current flow. We do have attenuation. Attenuation is over time or distance, does the signal degrade? The longer the electrical signals have to travel, the weaker they get. Many years ago, they thought that radio signals in space could travel forever. It has recently been proven that they also degrade and they do not travel forever. Electrical signals are susceptible to interference from two sources, and these sources they can distort and corrupt the data signals. Electromagnetic interference, EMI, and radio frequency interference, RFI, and also crosstalk, which we will talk how that comes about. When we choose a technology, we have to take into consideration where is this cable being run. If I'm running copper cables through someone's house, it's probably not going to have a lot of either EMI or RFI to corrupt the signal. If I'm running the same type of cable through a welding shop, I'm going to have a tremendous amount of electromagnetic interference. So maybe I would want to choose a different type of technology. To mitigate problems with data getting corrupted, we need to have adherence to the cable length limits for the different technologies. Different types of copper cabling can mitigate both EMI and RFI by using metallic shielding. And some kinds of copper cable mitigate crosstalk by twisting opposing circuit pairs of wires together. Now, if we look at an electrical circuit, this is the symbol that we use for a battery. This is the symbol that we use for a resistor. It does not necessarily have to be a resistor, but it could be a device. Could be a light bulb. This could be a flashlight. The longer line on the battery is positive. The shorter line is negative. When we have a complete connection, as I have shown, electrons, electrical current, flow from the negative back to the positive. This is referred to as electron flow because it is the physical movement of the electrons. Originally, scientists thought that something came from the positive and went to the negative. And we now know that that is not the case, but we still refer to that as conventional current flow. But the actual flow is from negative to positive. Now, when an electrical current flows through a wire, surrounding the wire, you have magnetic lines of flux. Now, because the current flow goes in the opposite direction up above, the magnetic lines of flux are exactly opposite. So if I take these two wires, one going out, one coming back, and twist them into a pair, one magnetic field cancels out the other magnetic field, and we eliminate crosstalk. At the end, where it goes into a connector, the wires obviously can't be twisted. So here, they may be straight. And because we have multiple pairs connecting into a connector, the magnetic field from one might cause crosstalk on one of the other pairs. You have probably all heard a form of crosstalk making a telephone call, in that you hear another call or people's voices in the background. That is also a form of crosstalk, usually coming from wires that are not twisted and therefore do not cancel one another. The most common type of copper cabling is unshielded twisted pair. And you notice we have four pairs of wire. We have a blue, an orange, a green, and a brown. And with each one of these, you have a solid color and one that is white with some sort of a blue stripe. Orange and an orange or white with an orange stripe. Green and green with a green stripe, so that we can identify the pairs. There are multiple types of UTP cable. If you were to go out shopping for a box of 1,000 feet of unshielded twisted pair, you would have two choices. Straight unshielded twisted pair, which may cost you about $100 a box, and a type referred to as plenum, and that would cost you about $250 a box. They both look the same. The difference with plenum is that the material in the plastic does not give off toxic fumes in the event of fire. So we have to use those in, or that type of cable, in areas where people may be um, overwhelmed in the case of a fire by the fumes coming from these cables. To try to eliminate either EMI or RFI, we can also have a shielded twisted pair. And as we can see, we have a foil. Each of the pairs may also have foil around them. At one end of the cable, we connect the foil to a ground connection. It is only done at one end because we do not want the foil to become a conductor. Coaxial cable, which you are probably familiar with, this is what cable TV normally runs on, has an outside jacket of copper, maybe a copper braid, has some type of flexible foam, and an inside conductor. The fastest that we can run this would be at 10 meg. Unshielded twisted pair, it is very common to run that at gigabit speed. Also, with coax, We run this at half duplex. Half duplex means that we send data in one direction, we have to stop, and then data can be sent in the opposite direction. So even though it's 10 meg, you would effectively be getting about 5 meg in each direction. And as we factor in the amount of overhead, it even reduces the amount of good put much less. With either unshielded twisted pair or shielded twisted pair, we can use one pair of wires to send data and another pair of wires to receive data. This is what's referred to as full duplex, where we can send data in both directions at the same time. So if I said this was 1 gig, I can get 1 gig going out and 1 gig coming back. As we can see here in our diagram, we have the twisted pairs. It's the most UTP is the most common networking media. We terminate it with an RJ45 connector. It interconnects hosts with intermediary network devices, our switches, routers. The key characteristics: the outer jacket protects the copper wires from physical damage. The twisted pairs protect the signal from interference, and the color-coded plastic insulation electrically isolates the wires from each other and identifies each pair. One of the things that we also must consider with any type of wires, whether it be fiber or copper, is the resistance. Resistance is symbolized by omega. Resistance to the movement of electrons in the copper. If I want maximum power transfer going from the cable into a connector, an RJ45 connector, and into my device, the resistance of the wire must be equal to the resistance of the connector. And that gives us maximum power transfer. Now, we use this same theory in that if these two do not match, some of the signal does go through. Some of the signal gets reflected back. And if we know the speed that the signal is traveling, we can tell the distance to that point. If I took a cable that is connected to nothing and I put it into a device, handheld device, referred to as a time domain reflectometer, if it goes to nothing, the resistance goes from whatever the resistance of the wire is to an infinite resistance, so that the entire signal gets reflected back. Knowing the speed that the signal travels and how long it takes to get back, the TDR will tell us that this cable is, for example, 40 feet long. You may have seen the phone company digging up the street looking for a break in the cable. How do they know where to dig? They went to the endpoint and they put a time domain reflectometer, and it told them the break was 100 feet from where they were. And that gives them a good idea of where to actually dig. For fiber cables, we use the same process, except we use an optical time domain reflectometer. In a corporate environment, the documentation should tell you how long a particular cable is. If you put the TDR on the cable and it tells you that it is not as long as in the documentation, you now know that you have a break in that particular cable and approximately how far from where you are the break actually is. In shielded twisted pair, you may have a shield that surrounds all four pairs, and each pair may also have a shield as well. As I said earlier, only one end of the shield is connected to ground. This gives you much better noise protection. It is more expensive than UTP. It is harder to install. It is terminated with the same connectors though, and it interconnects hosts with intermediary network devices. The key characteristics of STP, shielded twisted pair cable: the outer jacket protects the copper wires from physical damage. The braided or foil shield provides EMI or RFI protection. A foil shield for each pair of wires also additionally provides EMI and RFI protection. And the color-coded plastic insulation electrically isolates the wires from each other and identifies each pair. There are many types of cable. You could have a cable that is meant to be buried, and within the jacket, the pairs of wire are surrounded by a silicone gel to prevent moisture and corrosion. Coaxial cable: you have an outer jacket that prevents minor physical damage. You have the woven copper braid or metallic foil, and that acts as a second wire in the circuit as a shield for the inner conductor. A layer of flexible plastic insulation, and then a copper conductor in the middle. Some of the connectors you may have seen before. The F-type is most commonly seen for cable television. The N-type is most commonly used in wireless, going to an antenna. The BNC you see many times in networks that use coaxial cable. It's very rare these days to see a network using BNC connectors. They were not easy to put on and much more expensive. Besides, they took a tremendous amount of room on the intermediary device. If we were to take a look at a modern switch with RJ45 Ethernet connectors, we may have a switch with 48 connectors. You would not have the same size switch with 48 connectors for a BNC. Now here's a good picture for the UTP cabling. And you can see the blue has more twists per inch than the green or the brown or the orange. And this is specifically done, again, to eliminate crosstalk. So UTP has four pairs of color-coded copper wires twisted together and encased in a flexible plastic sheath. There is no shielding in unshielded twisted pair. UTP relies on the following properties to limit crosstalk. First, the cancellation effect. Each wire in a pair of wires uses opposite polarity. One wire is negative, the other wire is positive. They are twisted together, and the magnetic fields effectively cancel each other and outside EMI and RFI. Variations in the twist per foot in each wire. Each wire is twisted a different amount, which helps prevent crosstalk between the wires themselves. There are many types of UTP, such as Category 3. You notice the wires are not twisted. The most popular place that you see this is in telephone systems. A Cat 5 could go up to gigabit, and the very latest, a Category 6 cable. Now, this diagram is not the best because it looks as though the wires are shielded. They are not shielded. If we were to look in the end of the cable, there is a plastic insert that keeps the 4 pairs of wires separate. And as such, we can run Category 6 at much higher frequencies. Now, the standards that we use to wire these are the TIA EIA 568 standards. And the standards will give us the cable types, the lengths, the types of connectors, how do we terminate it, and how do we test it. The electrical standards for copper cabling are established by the IEEE, and that rates cable according to its performance. So Cat 3, Cat 5 and 5E, Cat 6. Again, these are regulated by the IEEE. How we put these into a connector is regulated by the TIA EIA. As we can see here, this is the most common, an RJ45 connector, and it may be put onto the end of a cable, or it may also be as a socket. This example is a very poorly terminated UTP cable. Too much of the cable is untwisted. Plus, the jacket that gives you strength when pulling a cable, installing a cable, the jacket should have been up inside the connector as shown in the bottom. You want the jacket inside so that when this plastic piece is crimped, it holds the cable in place. You want the ends of the cables to go all the way to the very front. These brass leads look something like this. So when the cable is put into place and this is crimped, these points go into the conductor. Now, when we wire a cable, we use either the 568A or the 568B standards. If both ends use the 568A or the 568B, is referred to as a straight through cable. Straight through cables go from either a host to a switch as a network device. They have to go between unlike connections. So I may go from a router to a switch. I may go from a host to a switch. Routers and hosts have the same type of interface, so that would be the same. If I'm going between two routers or two hosts, or between a router and a host, I would want one end being the 568A and the other being a 568B. That creates what we call a crossover. If we were to take a look at the wires, on one side I would have a receive and a transmit. On the other side, I have a receive and a transmit. A straight through cable, the receive would be going to the receive and the transmit going to the transmit. Think of receiving a call on your cell phone, and if you receive the call, you have to turn the phone over so that you're listening to the microphone and talking into the speaker. Not a particularly good idea. The crossover takes the transmit and sends it to the receive, and the other transmit sends it to the receive. So you can see why we refer to it as a crossover. Many pieces of equipment today have MDIX. MDIX electrically checks the type of cable that you've connected, and if you've connected the wrong cable, it electrically changes the property in the connection to make it work. Not all devices have MDIX, so you really need to know what type of cable to use in different situations. The last on our list is the rollover. This is a Cisco proprietary cable, and it's just a totally flat cable. So on one side, I guess it goes from 1 to 8. On the other side, it goes 8 to 1. There is no twisting, there is no cancellation, because this is only for low speed programming of an intermediary device. We normally connect from the serial port of a computer. If your computer does not have a serial port, we usually use a USB to serial adapter. We then plug the rollover cable into the serial adapter, and the other end will have a RJ45 that plugs into the console port of the device. Fiber optic cabling is not as common as UTP because of the expense involved. It's ideal for some networking scenarios, such as if I am running a cable under the ocean, I do not want to use copper because of the corrosion of the salt water. So fiber is perfect for that. If I'm running underground, fiber is perfect for that because of the moisture and the corrosion characteristics. It can run much longer distances at higher bandwidth than any of the others. It is less susceptible to attenuation and completely immune to EMI and RFI. I do disagree with this statement because it is not completely immune. In everyday use, yes, it is completely immune. But it has recently been shown if we put light through a very high intensity magnetic field, we can bend light. So that statement for the home networking and the environment that we normally run fiber optic cabling, yes, it is completely immune. But it is a false statement because we can bend light. It's made of very flexible, extremely thin strands of very pure glass. Even though it's flexible, that does not mean you can make a 90-degree turn. The diameter of the turn is regulated, and there are specific guides to use with fiber optic. It may use either a laser or an LED to encode bits as pulses of light. Now, as we mentioned those, you never ever look into the end of a fiber optic cable. Whether it uses a laser or an LED, the light will do damage to your eyes. Cards are made that you can shine the light onto the card to see if it's actually transmitting. But you never again ever look into the end. The power of the lasers or the LEDs will do damage to your eyes. The fiber optic cable acts as a waveguide to transmit light between the two ends with minimal signal loss. We still have signal loss. Now, if we took a look at single mode, the strand of fiber is very thin, and we use a laser to transmit. Single mode. So this uses a laser. Multi-mode is a much thicker cable, which allows us to put multiple signals in at the same time. If in a cable, whether it be single or multi, if the angle becomes too steep, some of the light is lost. Some gets reflected back. What we always look for is what's referred to as total internal reflection, that all the light is reflected back within the cable. But this does happen. Think of driving your car on the highway. If you were into an accident and you had to hit the Jersey barrier in the median, you would probably rather give it a glancing blow because you and your car would stay in the lane that you were in. If you hit it more head on, part of you may be in the lane you were in, and part of your car may be in the opposite lane. That's what's happening here with the fiber. In that if we come in at too steep of an angle, we lose some of the light out through the cladding of the cable. The only way to prevent this is to have an absolutely straight cable, and that never happens. You can have what we refer to as just a micro bend, just a sag in the cable. And as the signals come in, the angle changes so that we do lose some light. So this is a natural occurrence that you cannot totally eliminate. Here are some better diagrams of both single mode and multi-mode. Again, single mode, one signal at a time. Very small core, uses expensive lasers and long distance applications. If I have two buildings, we would normally use single mode to connect the two buildings. This is why it's normally referred to as horizontal cabling, because it goes horizontal between the buildings. Multi-mode, you'll notice single mode was 9 microns of the core. Multi-mode is 50 to 62.5 microns, about 5 times bigger. Larger core uses less expensive LEDs. The LEDs transmit at different angles coming in, and up to 10 gigabits over 550 meters, much longer distances. Single mode goes longer than multi-mode. Multi-mode we would usually use within a building, such as a tall building, to connect between the floors. As such, this is normally referred to as vertical cabling. Fiber optic cable is now being used in 4 types: enterprise networks for backbone cabling applications interconnecting infrastructure, fiber to the home, such as Fios, used to provide always-on broadband services, long-haul networks used by service providers to connect countries and cities, and submarine cable networks used to provide reliable, high-speed, high-capacity solutions capable of surviving in harsh undersea environments at up to transoceanic distances. Putting ends on fiber used to be a very expensive process in that you had to melt the glass and put it together. The instrument to do that was extremely expensive. Now, there's a simple tool that will just cut the cable, and then there is an end that has a gel that has the same optical properties of the cable that can be crimped on. Recently, Verizon updated the Fios connections to my house, and the technician was using that. And I was extremely interested, and he showed me how it worked. And it's actually fairly inexpensive and works extremely well. So the use of fiber, I would think, is going to be coming down in price and overall use very rapidly. Fiber, unlike RJ45s on Ethernet, has multiple different types of connectors. As we can see here, the straight tip ST connectors, a lucent connector, subscriber connectors, duplex multi-mode LC connectors. So that when you buy a fiber optic cable, it needs to match the type of connection that you have on your intermediary device, your router or your switch. Because obviously, as we can see just in this diagram, one will not fit into the other. You can purposely order cables with one type of connector on one end and another type on the other end, in case you have to connect between 2 different manufacturers' pieces of equipment that have different connectors built in. As we can see here, there are many types of fiber optic patch cords with different connection ends. Now, unlike Ethernet, where the outside color of the cable makes no difference, in fiber it does. Yellow is single mode. Orange is multi-mode. So we can see here the orange cables are all multi-mode, the yellow cables are all single mode. So a yellow jacket is for single mode fiber cables, and orange or aqua for multi-mode fiber cables. Ethernet cables, the outside color does not make any difference. Where I was working in New Hampshire, when I designed the network, I used different colors of Ethernet cables for the different type of data I was carrying, such as red I used for the video cameras, green I used for Ethernet, blue I used for trunk ports, yellow I used for the phone system. So we can use different colors to show what type of data are we actually transferring. If we take a look of fiber versus copper, bandwidth in copper can go up to 10 gig. Fiber, we can go up to 100 gig. Distance of copper, 100 meters maximum. This isn't to say that you couldn't run 105 and still have it work, but this is the recommended maximum distance. Fiber can go all the way up to 100,000 meters, 100 kilometers, about 60 miles. Again, immunity to EMI and RFI. Copper has very little immunity. But as far as the connector costs and the skills, it's the lowest. It's the easiest to put together. Fiber, again, I would not say completely immune, but in our everyday use for our network, yes, that's probably a true statement. But it is immune to EMI and RFI. It's also electrical hazards because the fiber does not conduct electrical signals. It is, though, the connectors are high in cost. With the older technology, yes, it was a high skill requirement. And safety has to be high because, again, the light will damage your eyes. The fiber will go into your skin and you can possibly become infected. So the safety precautions that we must take dealing with fiber are much different than the safety precautions dealing with copper. Wireless has become extremely popular. Carries electromagnetic signals representing binary digits using radio or microwave frequencies. Provides the greatest mobility option. Wireless connection numbers continue to increase. If we take a look at some of the buildings in the Northeast, we have many older former mill buildings with stone walls. To try to wire this with a traditional copper would be very expensive because we would have to drill through the stone. So wireless is very popular in this type of a building. The coverage area is effective coverage can be significantly impacted by the physical characteristics of the deployment location. The same wireless device in an older house with wooden studded walls, it will go further than in a more modern house that may have metal studded walls because the metal will absorb the signal more. What the walls are made of, all the other characteristics of the building will interfere with the wireless signal. And it is extremely susceptible to interference by other devices, such as electric motors, lightning, arcing. So back to the welding shop, that is going to create a lot of interference. Wireless is also inherently insecure because you're putting signals out over a public medium. Wireless communication coverage requires no access to a physical uh, strand of media, so anyone can gain access to the transmission. Even data that is encrypted eventually can be broken. It's just a question of how much time is going to take to break it. So, is encrypted wireless traffic totally secure? No. It uses the shared medium, operate in half duplex. And as we talked about earlier, half duplex is sending a signal in one direction, stopping, and then in the opposite direction. Some of the new wireless standards use two separate frequencies, and we can send and receive at the same time. The IEEE and telecommunications industry standards for wireless data communications cover both the data link and the physical. And in each of these standards, physical specifications dictate the data to radio signal encoding methods, the frequency and power of transmission. We are putting something out that could damage people. It's like a microwave oven without the walls. So the amount of power I can transmit is strictly regulated. The signal reception and decoding requirements and the antenna design. Is it a directional antenna or point to point, or is it an antenna that covers a different type of area? Some of the wireless standards, the IEEE 802.11, and under the 802.11 you have A, B, G, N, AC, AD, and others. Bluetooth is the IEEE 802.15 or a personal area network. WiMAX is 802.16, and that uses a multi-point topology to provide broadband wireless access. And Zigbee 802.15.4, very low data rate, low power consumption communications, part of the Internet of Things. As we see more and more devices that we purchase today are wireless enabled. I have a device to cook food using hot water, and I can control it from my phone because it's a wireless, and it looks just like a about a 1 foot tube, maybe 2 inches around, and you put your meat or whatever you want to cook into a plastic bag, sealed, and it's put into a pot of water. And you control the temperature through your phone and the amount of cooking time to get exactly what you want. And uh, it makes the meat or other things that you're cooking extremely tender. It's a very slow cooking process and works very well. But that's part of Zigbee in that my device connects to the wireless in my home. Now, in general, a wireless LAN requires the use of a wireless access point, and these concentrate wireless signals from users and connect to the existing copper-based network infrastructure. On your host, you need a wireless adapter to connect to that. And depending upon the technology that you're using, your adapter should be able to connect to your wireless access point. And these are all the different wireless standards. You can buy the latest router with the best standard, but if the network card that is in your laptop won't go up to that standard, you do not gain any of the benefits of having that very expensive, more modern wireless router. So network administrators must develop and apply stringent security policies and processes to protect wireless LANs from unauthorized access and damage. Think about going to the hospital. Most of the internal connections in the hospital are all wireless today. Think of the amount of data that somebody hacking into that could get on individuals. Security is a paramount feature dealing with wireless. Now, in business, we would have a switch that may have a wireless LAN controller built in, or it may have a separate wireless LAN controller attached. Coming out of the switch, we would have our wireless access points. This is more of a commercial system. When a user connects to the network, they don't associate with the access point. They are associating with the wireless LAN controller, which gives them mobility throughout, going from access point to access point, still authenticated by the wireless LAN controller. The wireless LAN controller will control these access points. We usually use 3 channels: 1, 6, and 11. The reason for those channels is that they do not overlap, so that we do not get into a situation where we're between channels. Then, this is very similar to the cell system. If I need to expand my network, I can add in another access point with the appropriate channel. The wireless LAN controller will do this dynamically. The access points that we normally use are referred to as LWAP, lightweight access point, versus a heavyweight access point. A lightweight gets its intelligence from the wireless LAN controller. A heavyweight has its intelligence built in, which means I would have to program this as far as power, as far as the channels. Hundreds of things would have to be programmed into each access point. Whereas using a wireless LAN controller, it will dynamically see this, dynamically see the distance between these, and adjust the power so that the network works most effectively. This is more of a commercialized system. This is one of the packet traces that you will be doing. This is a hardware lab that you will not be doing in this particular course, but if we were meeting in person, then we would be. This concludes Chapter 4, the physical layer.